In this section, you will study basics of iterative algebraic solvers. Let's get started with basic concepts. A general type of iterative process for solving the algebraic system AX equals B can be formulated as follows. The first step is matrix splitting. We write the matrix A in this form. A is m minus n. Here m is invertible. You'll see why the matrix must be invertible very soon. Then the system can be written in this form. A is m minus n minus nx is moved to the other side to get that one. In second step, now we can introduce an associated iterative algorithm by taking the old iterate to the right side to get new iterate in the left-hand side. Of course, the iteration should start with an initialization x0. Once m is invertible, then we can reach at this algorithm. To deal with this algorithm more conveniently in analysis, we reformulate the equation into either this one or that one. It is a simple algebra using the identity n equals m minus a. You can do it. You can check it quite easily. The matrix identity minus m inverse a, which is the same as m inverse n, is called the iteration matrix. Once you design an iterative algorithm, you have to make sure the algorithm converges. We'll say that the algorithm is convergent if it converges for any initial vector x0. The iterates x1, x2, x3, and so on will be computed by the algorithm, and our objective is to choose m so that these two conditions are satisfied. The sequence, the iterates, is easily computed, and that means that m must be invertible first of all, and then m must be easy to invert. And this second condition, the sequence converges rapidly to the solution. That means that m is a good approximation of a. Usually we say m inverse is a good approximation of a inverse. Then it means that the approximation is a spectral sense. It's around eigenvalue. So that eventually when you deal with m inverse a, then an eigenvalue point of view is around identity. Okay, we rewrite the algorithm here. Now we assume the iteration converges to a vector x. Then we can write in this way for x. Of course, this equation can be obtained from ax equal b without introducing the iteration. If you just use the matrix splitting, then you can reach at that one. Assuming x is the exact solution, you can reach this one. Okay. Now we subtracted this equation from this one. Then left-hand side, x minus xk, we define ek to be x minus xk. Then from these two equations, ek is the metric times ek minus 1, and these two terms are the same, and so it's cancelled out. So we reach at this error equation. Now let's try to measure the magnitude. Norm of ek is bounded by norm of this metric and norm of this ek minus 1. Of course, again, norm of ek minus 1 will be bounded by now norm of this one and then ek minus 2. So we reach at this one and continuously, so that at the last moment we reach this term. So we can easily see that once this norm is less than 1, then now no matter what it is, as far as it is bounded, you can see this norm is converging to 0. So here, norm of the iteration metric is strictly less than 1 is a sufficient condition for convergence of the iteration. Once the norm is strictly less than 1 for any induced metric norm, then the sequence produced by the algorithm converges to the solution of ax equals b for any initial vector x0. So that is a sufficient condition. That means with some other condition also it can converge, although norm is larger than or equal to 1. So it is a sufficient condition. Now, before saying the equivalent condition for convergence, let's consider this note. We give the name for the norm of the iteration metric delta. Now, when we try to choose m, then m inverse a is around identity, or m inverse is a good approximation of a inverse, then identity minus the metric will be near around 0, which means delta will be small, so the iteration will converge faster. Now we assume delta is less than 1, which is a sufficient condition for convergence. Then we can say that this one, the xk minus xk minus 1, becomes smaller as iteration goes on. Indeed, here ek is this iteration metric times ek minus 1. Now we can rewrite this term into this one. Okay, let's see here. This is the same as x minus xk minus 1. So we write here x minus xk plus xk and minus xk minus 1. Then this portion is ek and that one. So we have this one. Now we take a norm. Left hand side is ek norm and right hand side. Okay, norm of this iteration metric is delta, and we separate these two vectors, ek and the other part, measure the norms separately. Then we have this inequality. And we move this one to the other side and solve for EK norm, then we reach this inequality. This means that the norm of consecutive iterates can be used for stopping criterion. Once it is small, then even though we have this scaling factor, the error, real error, is small. So that by using this one, we can stop the iteration. For example, if you want to get 10 to the minus 5 error tolerance, and the error must be less than 10 to minus 5, then you may choose a tolerance for this difference, like 10 to the minus 6. Then with this factor, now it may get real error 10 to the minus 5. Depending on the delta estimated, you can choose a little bit the stronger condition for the difference. Then you can get the desirable accuracy. Anyway, the key point is that the consecutive iterates can be used for stopping of the iteration. Here we have a theorem. The iteration converges if and only if the spectral radius of the iteration matrix is strictly less than 1. Spectral radius is the largest eigenvalue in modulus. So once the spectral radius is strictly less than 1, then all is convergent. And also the algorithm converges, then spectral radius of the iteration matrix must be strictly less than 1. The iterative algorithm converges if and only if the iteration matrix is convergent. For the concept of the matrix convergence, you can see the theorem earlier we studied. We'll consider an example of iteration, which is Richardson method. Richardson method is the simplest iterative algorithm. In the method, M is simply chosen to be the identity matrix. M is identity, so the N must be identity minus A. If you drive the iteration, then you can iterate this one. From old iterate, just simply we're adding the residual, then we can get new one. It's the simplest algorithm. In this portion, we are getting the residual, the line by line. But in modern implementation, you can implement this one in metric vector sense. So that quite easily you can implement. But I implemented here to show details and update also pointwisely the updated. By using the algorithm, your A is defined. The first row, second row, third row, and divide by 6, and B is 11, 11, 11, a vector, and divide by 6. After making this matrix, I chose the true solution 1, 1, 1, then addition is 11, addition is 11, again 11. So the true solution is 11. And then I scaled the A and B by using 1 over 6, so that yet the solution is 1, 1, 1. Okay, by using the algorithm, and the iteration is done 10 iterations. Okay, we reach here on the bottom, not at 1, 1, 1, but anyway, it is approach to the true solution. It is slow. It is simple and it is slow. But however, in some cases, the method is working very nicely and also yet being used there. We check the eigenvalues of the iteration matrix, identity minus A. Then there are 3 eigenvalues, 1 real and 2 complex valued. And in modulus, this one is the largest one, 0.8333, so that spectral radius of the iteration matrix is strictly less than 1. From this one, we can get the eigenvalues of A, and so that here, and these eigenvalues are inside the open disk in the complex plane. Around 1, we make a circle, and that is inside the circle. So that is in disk radius 1, and centered at here 1, and so this disk is like that. So inside, excluding the boundary, every eigenvalue is inside here. And the method is convergent only if every eigenvalue of A is inside this disk, is sufficient and necessary condition. Every eigenvalue of A must be inside here. Now, if some eigenvalues of A are not in the disk, that disk, then you may multiply eta is a scaling factor such that now every eigenvalue is inside this disk. Then you can apply now Richardson method. And if you apply Richardson method, then M is again identity, and N must be identity minus eta I, eta A. Eta A is now the new matrix. So therefore, this one, we are applying the Richardson method. Then with some algebra, you can reach this algorithm iteration. Only the difference from the original one is now eta. So earlier, this algorithm is updating using the residual. Now, scaled residual for this system, and eta scaled residual is added to get new iterate. So once the eigenvalues of the eta A is inside the disk, all eigenvalues, then now this will be convergent. So if you can choose such a scaling factor eta, then you can use the Richardson method. Here is a self-study problem. If A is a definite matrix, then you can prove that the generalized Richardson method is convergent for the solution by taking eta appropriately. A definite matrix means that, okay, and eigenvalues are either positive, all eigenvalues are positive, or all eigenvalues are negative. Once all eigenvalues are negative, then it's negative definite. Once all eigenvalues are positive, then it is positive definite. Anyway, definite matrix means that eigenvalues are one side. and here the y-axis and the vertical axis in complex domain, complex plane, only in one side, either this side or the other side. And but definitely means that, in fact, the real eigenvalues, positive eigenvalues or all negative eigenvalues. Then we say it is a definite metric. For such a metric, you can choose eta appropriately to get a convergent generalized Richardson method. You can do it yourself. Okay, that's the end of the section. Thank you.